very good morning and welcome to the second week in the course on Foundations of Continuum Mechanics. This week we will start with the permutation symbol. So let's get started. So today in this lecture we'll be talking about two topics. The first one is the permutation symbol. We'll be defining the symbol and learning how to use this in tensor algebra. And we'll also be talking about the epsilon-delta identity, which is known as one of the most important identities in a course in the foundations of continuum mechanics. So let's start with the definition of the permutation symbol. So the permutation symbol epsilon has got three indices. So I'll write it as epsilon ijk. So epsilon ijk is defined as, so it takes the value 1 if the indices I, j, k appear in the order of 1, 2, 3 and so on. So the order has to be cyclic. So it's 1, 2, 3, 1, 2 dot dot dot. So what that basically means is that if I have epsilon 1, 2, 3, so that follows the order as given here. So that will be a 1. So we'll discuss more about it, but let's complete the definition first. So epsilon ijk is minus 1 if it follows the order such as 1, 3, 2 or 2, 3, 2, 1 or 2, 1, 3 and so on. And it's equal to 0 if any two indices repeat. So let's take some examples. So I've given you one example where we've written epsilon 1, 2, 3. Let's take a few more. So let's take epsilon 3, 2, 1. So in this case, if we look at the definition, then if you look at the ordering, you have this 3, 2, 1. So it follows this order. So it's a minus 1. In fact, what we can do is we can draw the indices like this. If I say 1, 2 and 3. So this is called the cyclic order. So in this case, the value is going to be 1. So you can check if the order is 1, 2, 3. It follows the order as shown in the cyclic order. It could be 2, 3, 1. So 2, 3, 1. So again, same order. It could be 3, 1, 2. So that's again the same order. Okay, so that's the reason we wrote as 1, 2, 3, 1, 2 dot dot dot. So on the other hand, in the case of an anti-cyclic order, we'll have the other way around. So 1, 3, 2. So this order is 1, 3, 2 or 2, 3, 2, 1 or 2, 1, 3 and so on. So this is an anti-cyclic order. And in this case, the value is equal to minus 1. So we should say epsilon is equal to minus 1 and here epsilon is equal to 1. I'm writing epsilon, but epsilon typically has 3 indices which will define the order and the value. So let's take another example. So what is epsilon 1, 2, 1? Now in this case, it goes into the third case where it says that if any indices repeat. So in our example that we've just shown, it's 1 to 1, so the index 1 repeats. So by that, this becomes equal to 0. Right? It's quite straightforward. So there's no confusion here. In fact, if I say epsilon 1 1 1, even then this is 0 because the index 1 repeats. All right. This symbol epsilon is also known as the Levi-Civita symbol. So in some texts you may see they may write the Levi-Civita symbol. So that's basically referring to the permutation symbol epsilon. And the name permutation is also quite straightforward because we are following a certain order. So that's the idea of having permutation in the name. So now that we've defined the permutation symbol epsilon, let's look at an important identity. And the identity says that if I swap any two indices in a given epsilon, its sign will change. So in general, I can write epsilon ijk is the negative of epsilon ikj. Again, this is quite obvious, but we can test it. So if we have I equal to 1, j equal to 2 and k equal to 3, so that's a 1. But if I swap j and k, so this becomes epsilon 1, 3, 2, and you can see that now the ordering has become anticyclic, so this becomes equal to minus 1. So you can check for any values of I, j and k, and this will hold because this is an identity. Now if any two values are equal, then both left and right sides are 0, which still ensures that the identity is satisfied because 0 is equal to minus 0. Also, because the ordering is the same, so for a general case, we can write, although this does not follow from the identity, but from the definition of epsilon, so we can write epsilon ijk is the same as epsilon jki, which is the same as epsilon kij, because in all three cases the ordering is still the same. Now I, j, k can take any values in this general expression, but whatever values you substitute for I, j and k, all these three will be equal for those values. Now that we have this identity in place as well, let's talk about the motivation of discussing this permutation symbol. So I'll start with some intuition. So let's look at the cross product of unit vectors e1 and e2. Let's draw these. So in the three-dimensional right-handed Cartesian coordinate system, the three unit vectors are given as e1, e2 and e3. So if I take the cross product of e1 and e2, I get an e3. So what's the order? The order is 1, 2, 3, and epsilon 1, 2, 3 is equal to a 1. Let's take another example. If we take e2 cross e3, so if you look at this figure, you can see that e2 cross e3 is from the right hand screw rule, it's e1. So this again, I can see epsilon 2, 3, 1 is also equal to 1. Let's change the order. So if I take E1 cross E3, so again look at this figure on the right hand side, you can see that E1 cross E3 is a minus E2, and if I take these indices epsilon 1, 3, 2, that's a minus 1. Right, and if any two indices repeat in the sense that if I have E1 cross E1, that's a 0, so that will be a 0. Well, this is so the motivation of talking about the permutation symbol is basically vector cross product, but I've just told you through an intuition. We will do it more rigorously now. So after we have seen this pattern of indices, this all this actually can be written more generally. So we'll say more generally, I can say EI cross EJ dotted with an EK is equal to epsilon ijk. So that's another way to define epsilon ijk, the permutation symbol, using unit vectors that we have done here. In fact, this is a very important expression, so I will put it in a box. So I leave it to you to figure out that this boxed expression is a more general expression of the above expressions that I have written. In fact, the easiest thing to do is you just put the values of indices as we have in this case, or this case into the expression and try to understand the situation, the motivation. Why not? Let's do it. Let's check this boxed expression for different values. So let's take the values I equal to 1, j equal to 2, and k equal to 3. So what's the left hand side? We have E1 cross E2, that's an E3. So E1 cross E2 dotted with an E3. So what is this? So E1 cross E2 is an E3, and E3 dot E3 is a 1. And we can see the right hand side epsilon 1, 2, 3 is also equal to 1. Right? Let's try I equal to 3, j equal to 1, and k equal to 2. So epsilon 3, 1, 2, so that's the same cyclic order, so that's a 1. What is E3 cross E1? Let's draw the unit vectors. So E3 cross E1 is an E2, and E2 dot E2, because k is 2, is equal to 1. So this still works. Of course, it should work because it's an identity. In fact, we can try with I equal to 1, j equal to 2, and k equal to 1. So if I is 1 and j is 2, so E1 cross E2 on the left hand side becomes an E3, but E3 dot E1 is a 0, right? And let's check epsilon 1 to 1. Well, that is a 0 by definition of epsilon, because if any two indices in an epsilon repeat, then its value is 0. So this is a very important identity, because this helps us define epsilon using unit vectors EI, EJ, and EK. So let's actually do something with this identity. So let's call it A. Before, I'll not tell you right now what I'm trying to achieve. We'll just take it as an exercise in tensor algebra, and then we'll get to an interesting result towards the end. So let's take the expression A. So I'll say an interesting exercise. So EI cross EJ dotted with an ek is equal to epsilon ijk. Just rewritten a here again. So you multiply both sides with an ek. So left hand side in this expression a is actually a scalar, and so is the right hand side, right? So we can multiply a scalar with a vector. So I will multiply this whole thing with ek. So that will become epsilon ijk times ek. Now the beauty of tensor algebra is that I've multiplied this with ek, but now k is a repeated index, although earlier k was a free index. But now that after this multiplication k becomes a repeated index, so I can expand using the summation rule. Okay, it's a little subtle to understand this, but you will eventually get to it. But that's the beauty of this notation, that I can multiply with an expression involving an index on both sides. But now that if the index is repeated, so the summation is implied over it. Right. But we'll not do that. We will use another approach which will simplify things rather than expanding it using brute force. So the left hand side of this expression is ek, and I'll call ei cross ej as ep. That's for just for convenience. So I've taken ei cross ej as ep, just to save some space. That's it. So this is left hand side, but since all these are unit vectors, so I can write ep dot ek as delta pk. That's from the dot product between two unit vectors is actually defined as delta pk, as we saw last week, and we have an ek here. Now in this we can apply the delta substitution property. So what that will do is we'll get rid of this k, so this becomes ep. Now what is ep? Ep actually was ei cross ej, so this actually is ei cross ej. So I have obtained the left hand side. Now let's see what the right hand side is. Well, the right hand side is, there's no simplification happening on there, epsilon ijk ek. So let's write it down. So starting with the boxed expression a, what we have got is ei cross ej is equal to epsilon ijk ek. Now that's a very important property as well. In fact, this property that we have in front of us is the generalized way of writing vector cross product. Just as we learned to write ei dot ej as delta ij, we have used the permutation symbol to be able to write the cross product between ei and ej. So ei cross ej is epsilon ijk ek. So there is no need to write determinants that we typically do while writing cross products, while expanding cross products. Whenever we have a situation where we have to have cross products between two vectors, although we'll discuss it next lecture, but this is laying the groundwork for defining vector cross product. So this expression number b is that will help us to write vector cross products using indicial notation. That we'll do next week. This lecture, I would want to work more on the mathematics of the permutation symbol, because that's key here. We work with epsilons a lot in tensor calculus. In fact, the permutation symbol does not appear by itself. In many relations mathematically, you will see products of epsilons. And this is where the epsilon-delta identity will help us. So this identity links the products of epsilon to a products of delta, which greatly helps us to simplify expressions. And of course, epsilons appear as a result of cross products between different vectors and tensorial quantities. So let's write the definition of this identity. So if you have product of two epsilons, so I'll write epsilon ijk, epsilon pqk, then this is equal to, so let me write it down and then I'll explain and discuss it. So this is the products of epsilons on the left hand side, and we have products of deltas on the right hand side. So one important condition to be able to apply this identity is that the last index in the two epsilons on the left hand side has to be the same. This is important. If this is not the case, then the identity does not hold. Now, how do we remember this identity? It's not that difficult. The way I remember this is, and in fact, you need to remember this to be able to solve problems. So in this course, you'll be expected to remember this, but when you use it a couple of times, it will become a second nature. You don't have to stress yourself to remember it. So the way we use this identity is, so we have three indices, ijk here and pqk. So first you check whether the last index of both epsilons is the same. If that is the case, we proceed. So we say delta ip, so we call it the delta first. So the first index of the first epsilon to the first index of the second epsilon, so that is delta ip. Then we have delta jq, so that's the second. So the second index of the first epsilon is j and the second index of the second epsilon is q. So delta first times delta second minus, and then we have iq, so that is first second. So I is the first index of the first epsilon and q is the second index of the second epsilon, and then we have jp, so that is second first. Okay. So delta first times delta second minus delta first second times delta second first. It's quite straightforward. I'm sure when you think about it and try to apply it, you should be able to remember it. Right, so this epsilon delta identity is very important. You must remember it. I'll say must remember this. Now we will not prove it right now, because proving the identity requires the knowledge of some more mathematics that will be discussed later in this course. So we will leave the proving to later, but we will prove it later in this course. So the aim today is to learn how to apply the identity to solve problems. So let's do that. So let's take an example. So we have product of two epsilons, epsilon ijk, and we have to expand, or we should say simplify. We have to simplify this expression. So first we check whether the last index of both epsilons is the same. In this case it is. So we will apply the epsilon delta identity. So this is equal to delta first. So the first index of the first epsilon and the first index of the second epsilon. Now they happen to be the same, but that's okay. We are just applying the identity without thinking too much. Now delta second, which is delta jj, because j is the second index in both epsilons, minus delta first second, so that becomes ij, and then delta second first, so the second index of the first epsilon and the first index of the second epsilon. I'm sure now you're getting excited because you already know how to simplify this further because delta I is equal to 3 as we have seen last week. Delta Jj is also 3 from the definition of delta by applying the summation convention. Now this delta Ij times delta Ji, we can use the delta substitution rule. So that simplifies to delta II. So this becomes 3 times 3 9 minus delta II is a 3. So this is equal to a 6. So that's the simplified expression. So you can see that epsilon ijk simplifies to 6. Let's try another example. So we have epsilon jki times epsilon pqj. Now let's take the last index. Well, in this case, the last index is not the same, so we will have to make it the same. And the way we do it is because we know that if we ensure the same order of indices, they can be moved around. So we do rearrangement. So we will try to move this j towards the end. And the way this works is you have the order jki. So this is the same as the order kij. So I can write this as epsilon kij, and the second one stays as it is. So I'll say here this is rearranged. And now we can see that the last index in the two epsilons is indeed the same. So we can apply the epsilon delta identity. So this becomes equal to delta first, so that is delta kp times delta second, so that's delta iq minus delta first, so that's delta k times q and delta second first, which is delta ip. So in this case, there is no further simplification, so we leave it at it. So the whole idea of presenting this example to you was to ensure the fact that we check that the last index of the two epsilons is indeed the same, and if it is not, that's not the end of it, because if the index appears in the expression, you can simply do some rearrangement to get to the situation where the identity can then be applied. So if you had simply expanded or if you had applied the epsilon delta identity without thinking too much, you would have been wrong. So you have to make sure that the last index of the two epsilons is actually the same. So let's solve a few more examples. So can we apply the identity here? The last index is not the same. So what we'll do is we will rearrange the second epsilon. So we'll call it epsilon ijk times epsilon ijk, because the ordering is still the same order ijk in the second epsilon, and this is something that we just saw, that this was equal to from the previous case where we had epsilon ijk, that's a 6 from here, right? So this is 6. So you can see that this was exactly the same as what we had earlier. Let's try one more example. So we have two epsilons multiplied to each other, and we also have a delta. Now one way to do this is to apply the epsilon delta identity by doing rearrangement first and then expanding over delta. But the easier thing, well, you can try both situations and figure it out yourself. But what is typically easier is that first you apply the delta substitution property and get rid of one of the indices. So in this case, we have two indices p and r. So what I'll do is I'll replace an r with a p in the expression. So this becomes epsilon ipq, epsilon iqp. So this is after getting rid of the delta by applying the delta substitution property. And this can now be rearranged. So I have an epsilon ipq and I have an epsilon iqp. So rather than now this is where experience comes. So rather than trying to make the last index the same and applying the identity, we can actually see that we can swap P and Q because we know the identity that epsilon I j k is minus epsilon I k j, right? So we know that from the identity we had discussed earlier, because if you swap any two indices, the ordering changes. So that means that I can write this as epsilon I p q, and if I swap the indices p and q here, this becomes I p q but with the negative sign. So we have epsilon I p q, epsilon I p q, that's the same as epsilon I j k, sorry, this one, and that is equal to 6. So this becomes a minus of 6. Okay, so if you know values of intermediate expressions, you can do this swapping of indices to make the expression simpler. Again, this comes with experience, and that is the reason I reiterate that you should practice as many problems as possible to get an understanding and an experience with these identities. So they should become your second nature when working with continuum mechanics. So this brings us to the end of this lecture. So today we learned about the epsilon, that is a permutation symbol, and we also learned about the motivation behind the permutation symbol, that is the vector cross product. Towards the end, we talked about an important identity that's called the Epsilon-Delta identity, which is one of the most important identities in this course, which allows us to link product of epsilons to products of deltas, and that makes simplification very, very easy. So next, in the next lecture, we will use the permutation symbol epsilon in vector cross products and discuss higher order tensor products as well. So thank you, and I'll see you in the next lecture.